Good morning, everyone. Thank you very much, Professor George Wan, and organizers of this workshop for this excellent opportunity to bring us all together. I'm so glad to see so many friends, colleagues, and potentially future collaborators. So, as Professor Xu mentioned earlier today, this is perhaps a continuation of some of the discussions that we had back in Auckland in August last year, but also I'm sure will maybe inspire a lot of more discussions, new conversations as we're seeing just now. So I'm a working colleague of Professor giving us a lot of insights and asking a lot of questions. Maybe not many of us have answers at the moment, but I had the advantage of actually my office is next to him. And very often I could have the opportunity actually taking questions to his office and get answers. So you'll see perhaps a lot of the slides that I will in a minute will have the trace of the discussions that we already had today, but also maybe put into a more specific and maybe practical sense. So bring back some of my experience working in industry. Okay. So my topic today will really ask us some questions around how human and the machine perhaps will work in the future in manufacturing. Just pay attention to machine here, it's not robot only. So really looking at how the interface or relationship between human and the machine will look like in manufacturing. Okay. And I put it as thought and exploration because I believe lots of researchers here is actually working in this area. And it's a fast approaching area evolving very rapidly. So the work that we are presenting here is more of our thoughts. And I'm sure there may be a different version or maybe a different opinion from somewhere or someday. So to keep it short, if you like where we are discussing just now about Industry 4, Industry 5, I put on the left-hand side this famous diagram there around how manufacturing paradigms can be changed over the years. And it was really excellent to put into context of product variety and volume on the y-axis there on the left-hand side. So there was a belief there's a change around how manufacturing over the years will move from craft manufacturing all the way to mass customization, as Professor Xu mentioned. That was a main driver of Industry 4, and there was a really great desire for personalized manufacturing. So I had the opportunity before the academic job in University of Auckland. I worked in New Zealand factories for about 4 years. What I've observed in factories is a lot of New Zealand companies, they're very small, probably less than 50 people, roughly. But some of them are making really excellent products that are leading in particular niche fields. But if you look at the manufacturing mode of those factories, it's sometimes interesting to see that it's a blend of semi-automated tasks with a lot of manual work together to produce some world-leading kind of technological solutions. Okay, so I would say actually manufacturing in New Zealand maybe likely is a combination of craft manufacturing production, plus maybe some of the automation that we see under mass customization. But if you use the term around manufacturing New Zealand, maybe you can see one-of-kind production, you can see personalized production of that. So which actually motivated me to think, hey, how can we actually do better for manufacturers like that? Okay. So I'll come into that. Then on the right-hand side, you'll see this diagram around Industry 5, where European Union was thinking, hey, there may be a different way of looking at things, and the 3 pillars there. I'm not going to repeat that. But to me, when I was working in industry, I think the left and right, they're not in conflict. Okay? And a lot of times you are using technology solutions or creating technological solutions for purpose. So the right-hand side is perhaps around the purpose. So that's how I view it. So when we actually notice this revolution and notice these concepts, we really ask ourselves, what does manufacturing look like or can look like in the future? Coincidentally, about 1 year before the European Union's the fifth industry revolution vision, we put together a short paper and asking us, hey, can we treat people differently in manufacturing in factories? Okay? And how are we actually needing to treat them differently? Because in my view at that time, we are seeing whatever automation solutions you have, people are treated the same as machines. You put people alongside automated solutions there, people's working pace, productivity, working schedules all need to be designed really well in synchronization with automation systems down the track or upstream. Okay, so in that sense, we're doing lots of optimization research here, right? We're treating people the same as machines, and we're really not giving the options back to people of choosing how they work. But if you actually give the options back, the problem is, are we still actually running factories efficiently? Okay, because one of the biggest main drivers of factory optimization is costs. So how do you balance that? That's an unanswered question. But bearing that in mind, we had this idea around maybe possibly human and machine can work together. Okay? So working together in one way that say empathetic machines, they can really understand what human workers would like to do, what's their strength in skills, what's their personal preference, or maybe even say when do they want to have their tea break, okay? Or from day to day, I'm pretty sure that on Monday or Tuesday, maybe day after day, people's efficiency can be slightly different as well. So how do you actually work with that kind of uncertainty on the left-hand side around humans? So there are three aspects to look at: the physical state, the psychological state, and cognitive state. Now, right-hand side, in the empathetic machine, that really we think, hey, really machine could possibly be smart enough to observe changes in factories, observe human status. They make decisions autonomously, work together with humans. So there we call that the collaborative intelligence between human and machines. So that was thoughts around 2020. Then after observing the fifth industry revolution kind of vision, we really took the idea further and wanted to ask ourselves around, say, hey, what's actually been different in human-centric manufacturing, if you like? If in Industry 5, they say humans should be in the center of production processes, but are we not putting people in the center in the past? Or what's the other side of human-centric manufacturing? So I actually call it system-centric manufacturing, or past manufacturing systems. So really that motivated us to ask ourselves the first question: what are humans' fundamental needs in manufacturing? Why do we need to actually treat people differently? Or how different that could be, okay? The second is, what role manufacturers actually people play in manufacturing systems? And what's the difference taking those questions, okay? So based on that, in this paper, we, on the left-hand side, had a brief idea of really trying to understand, hey, what's humans' needs in manufacturing? And by looking at literature, by looking at some of the experimental studies reported by factories, we think actually in factories, there may be these 5 levels of human needs: safety, comfort, belonging, esteem, self-actualization. So when we look at human-machine relationship mapped to that, maybe in the past you'll see cold machines just sitting there at the corner of the factory and people doing separate tasks, so there's coexistence. There are cooperation there as well. For example, whenever we're looking at the CNC machine, digital human interface, you go there, operate the machine, leave it running, do something there yourself separately, then come back again. Then maybe it's a cooperation. But maybe a lot of time we're now talking about collaboration, maybe in shared workspace there. That perhaps it's cutting across level 2 and level 3. That's what we kind of put there. Then above all this, we want to say maybe can actually human needs of belongings of self-growth actually be emphasized, while not sacrificing system objectives like productivity. So how would that look like? Then we even mapped these industry revolutions on the right-hand side, try to think, hey, maybe there is some underlying logic behind it. Okay, so where you will notice that I put collaboration between level 2 and level 3, and where we see a lot of research now looking at, say, maybe increase the awareness of human motions, human fatigue levels, cognitive levels of that by looking at human robot or human machine task allocations. But on level 3, a lot of things like collaboration, real collaboration, involvement, sharing, and caring between human and machines that's not happening yet. So taking these ideas, we propose this high-level human-centric manufacturing system framework, where you can see that a factory in general have a dynamic manufacturing jobs with unique precedence relationships come in. So we say that there's personalized production requests come in. Then we come into a manufacturing system in general, where you have machines, have people working, they have different kind of attributes. Where you expect would be around personalized high quality products and workforce well-being, okay? But a lot of the conditions in the factory is probably around contingencies, okay? So there are lots of disruptions, lots of uncertainties there where you need to optimize and model and control, okay? But if you look, zoom into machines or workstations within a manufacturing system, you'll probably see a list of workstations in manufacturing systems where there are people and machines in general, as I described. Maybe that empathetic machine working together with humans will still make sense at workstation level. So one example could be human-robot collaboration working on assembly. So that on the right-hand side is something that we really need to understand, how machines can be smarter in general. Then on the left-hand side, how human and machines can work together. Okay? So on the system level, as Professor Shiosno mentioned, maybe things need to be able to be self-configured. So that's where we say, maybe that's one of the steps is first to connect the dots inside factories so that they are able to be configured. Second is, once you're able to configure manufacturing things, including machines, people, resources, jobs, work in progress, inventories of that, then you are facing a task of optimization. But that optimization may be slightly different from all sorts of kind of optimization we have seen before. It's dynamic scheduling and optimization, which is very difficult to solve, as we know. Second is you need to consider dynamic changes coming from humans. The last one is if, say, under optimal working conditions, something happens, say, one person just went to have a lunch break, okay? How do you still actually work together? So that we see maybe there's a self-healing mechanism that can really reorganize things dynamically and still work optimally. So now I would like to zoom into some of the technical thinking that we have along these lines. So if you really want to work together between human and machines or human and systems, so one thing is to really understand well about human. So obviously we like to think that maybe we can create a human digital twin to really understand the interesting attributes we want to see around human in factories. So there are three aspects that we have modeled. First is around ergonomics. That includes local muscle fatigue physically, continuous cognitive fatigue mentally. The second is capabilities, okay? So that includes your static kind of strength or skill levels. And third is preferences, your work habits, work patterns, task preferences, of that. So if we can understand all of that, that will give us a foundation to do any way of understanding human wellness, model it, and improve it. So inside this digital twin, we'd like to think the human digital twin and the human-centric HRC system as an example. There's a cyber-physical integration there. And using sensors, we possibly can understand those three aspects, just talk about human wellness, okay? So the sensors that we'd like to highlight here, maybe lots of us know some of the wearable sensors that we see around monitoring your body signals, right? And like to see that the sensors has to be lightweight, not really on human bodies, easy to use in factories. Okay, so I'm going to talk about that in a minute. Then, if you are able to actually create that digital twin, then can provide feedback back into optimization. So in that way, we can have fatigue sensitive task scheduling in manufacturing systems. We can focus on workstation level, maybe possibly have adaptive robot control to really work well with that individual human. Okay. So a little bit more into the specifics. In this diagram, if we say we have the opportunity to monitor human status, follow this perception line on the physical fatigue level, where we possibly can have an easy solution to monitor the fatigue of people's muscle strength. Then on the cognitive fatigue side, maybe we have some other sensors can work on that. So both of these cognitive and physical fatigue, they can come back to the human digital twin. But on the other side, on the right-hand side there, where there are actually dynamic manufacturing jobs we have to take care of, if possible, can actually, based on the fatigue level, allocate tasks dynamically to human and machines to work, then that would be lovely. So then we can establish that closed loop of monitoring human fatigue levels, optimizing it by control, okay? So my discussion technically will be more around the physical fatigue estimation, as well as the second part here of the task scheduling, right? So on the physical fatigue estimation, for some of us will know that in the past, if you want to understand how human workers felt after working, you probably run surveys asking, hey, would you feel after repetition of this task for half an hour, of that, right? So there's a subject kind of way of understanding fatigue. But also you can see these bulky sensors you can put on human bodies, like these EMG sensors you can put on your muscle, really take your muscle signal to really understand fatigue level. But none of these actually work really well to be able to accurately monitor fatigue, physical fatigue, because EMG signals, they require this really heavy and precise location of the sensor on your human body, but the surveys will be not accurate at all. So we ask ourselves, can we actually create a non-invasive kind of sensing techniques and really understand your fatigue changes over dynamic manufacturing operations? So our thoughts around this is, if we are able to establish some sort of muscle fatigue profile based on offline EMG signal sensing to calibrate people's muscle fatigue, muscle strength offline, then try to understand how fatigue is influenced by the load of the job, by the working time, by muscle strength, by the rest patterns, by the type of work you are doing. Okay, if we can establish that kind of equation, then are we able to actually monitor what the person is doing, then infer that kind of fatigue level using the equation that we can observe. So on the right-hand side, you'll see some experimental setups that we have, how we actually use surface EMG technologies to really understand that fatigue profile. Then, with that accurate fatigue profile, we can derive that relationship between fatigue and those factors I mentioned. Then we can has the opportunity to, just by observing what people are doing, then based on the fatigue profile, then in real time understand the fatigue changes. Okay, so this is the computer vision part, where just by observing the video clips of how people are doing things, in this case is assembling a bookshelf, then we can understand the boundary and repetitions of different tasks the person is performing. Then linking back to the fatigue profile, we are able to really understand the dynamic changes of physical fatigue. Okay, So the technical approach here, we use dual stream MSTCO network here to really predict the action boundaries between different tasks the person is performing. Because in the past, we couldn't actually achieve that using algorithms. So this is a performance in that bookshelf assembly scenario, where you can see on the bottom right, where we are able to understand the individual task the person is performing. For example, screw 1, screw 2, screw 3, screw 4, 100. So now, this is an example showing that you can actually then build optimization model, take into consideration of physical fatigue, you then work out the best kind of arrangement between a human and robot collaboration setup. So I'm not going into detail for time reasons, but please also remind me if we are over time. I think I have to finish on time before tea break. Okay. So that actually take us to some understanding around the system level kind of human-centric centric system, how that may operate. But if you look at fundamentally, yes, between human and system, they need to work together, but also at the workstation level, human and machines need to work together. Well, okay. So from Professor Xu's slides, there's a very important information there. So no knowledge is left behind, no human is left behind. So that actually lead us to some further thinking around, say, hey, can we actually develop really smooth, empathetic, compassionate relationships between humans and machines, so typically human and robots? So linking back to the level 4 and level 5 human needs. So we looked around, we look at a lot of research studies from different teams around human-robot collaboration as example, how smooth that can be, how really interactive and personalized can that be. So we don't see really good research there. But what we see is that, hey, if you want to achieve those kind of research, maybe they are missing some foundations. For example, can really machines really understand what human is doing and thinking really precisely? Okay? If you are in a context of high precision product assembly scenario, can you actually observe that really nicely? Because that's one of the kind of foundations to really allow you to put some interventions to human work. Okay? So in this example, you will see that this is what we had in our lab. The human and robot, in this case, doing some co-working together, but that's probably very similar to many other research teams that you can see a demo of how they work, okay? You have some technologies, but if you look at technologies or in these fields around human motion understanding, human intention understanding, prediction, or even task allocation, control, they're very limited. So we ask ourselves, we perhaps need machines to be able to understand the environment, understand really human that it is interacting with. So that's a self-awareness there. Second is we need to have dynamic coordination between human and machines, not based on fixed kind of schemes of how we work together. We really then, can we have human-machine empathy showing into activities that machines are performing? Taking robot as example, can you actually deliver the screwdriver to the right position to the person? Maybe the person is left-handed at the right time. Okay? And a human-machine co-evolution, where we are proposing that, say, hey, what if human and machine, when they really can understand each other, they become partners? They can learn from each other. Machines can train human what to do, how to do things nicely. And machines can also observe how different level of skills exist from different workers, then maybe to upgrade the machine skill as well. So a step further on this, you will say, yes, let's look at the safety first. On the right-hand side, the robot is able to avoid static obstacles while it is performing certain tasks. In this case, the human's left hand is a static obstacle, as you can see from the top right. Then from the bottom right, you can see that while in a simple scenario that human maybe want to approach something while the robot want to do something at the same time, then the robot can actually avoid people and giving people the priority without losing its objective, okay, by alternating its trajectories. So there's a simple illustration there. But we're actually missing something very important around human and machine understanding. So if we can have that human, in-depth human machine understanding, then we can actually do things much better than what we already showed you. So on that, we had this idea around human and robot or human machines perhaps do things very similar. So from the top, when engineers is shown a CAD file of a product to be assembled, the person will need to observe, learn, and then come up with assembly plan, then down to assembly actions that need to be executed. From a robot perspective, that may be following similar patterns. And between robot and human, we can actually, if possible, to transfer the knowledge between them. So in that way, we are able to give people the basic understanding. So have that in mind. We found that there's a lack of foundation for doing this kind of research. Therefore, in about 1.5 years, we spent a lot of efforts on creating this data set, on understanding, allowing people to understand assembly knowledge. So what we see that we really need a video data set that allow people to see the representative industrial assembly scenarios that displayed in those assembly videos. That actually videos actually need to also show some typical things that happen during assembly, during learning. For example, people tend to make mistakes. And people, when new people join a team, they will pick up skills at different pace as well. Then once they are skilled in something, they will be able to actually come up with new ways of doing things as well. So those patterns, we want to see that, because that shows actually different ways of achieving the same task by showing the skill progressions, showing people how they make mistakes, correct their own mistakes, because those are very important cues of understanding how people are thinking. Then also, what we found is a lack of consistent human-robot shared annotation that really down to the very granular level around which person is using what hand, which finger to do what actions using what tools. Okay? So have that in mind. We create these open source data set, have the box there, generic box there, that's showing the typical assembly features there. Then we collect the data from multiple views, multiple modalities through a 30 participant study. We collect and labeled all this data. Then we think, hey, that will allow us, if we can develop foundational video understanding techniques such as action segmentation, action recognition, object recognition, multi-object tracking, then will allow us to actually do reasoning from these assembly videos. For example, understanding the quality of your assembly work, understanding the progress of your assembly work, then track how you are actually collaborating with another worker, with another robot of that. So a lot of research applications can be enabled from there. So at a high level, this has been provided. We have more than 3,000 video clips and 3 views, 3 modalities, and we designed the assembly tasks on different plates of the box differently, and have 35 standard, non-standard industrial parts there using 4 standard tools as well. Then through these different staged kind of data collection, to actually encourage people to make mistakes, encourage people to do things differently, then to see how that may work, okay? So this is the box design. I'm not going into the details for time reasons. So this is all available open source. You can easily replicate this in your own lab. Or the source file is provided. And if you look at the assembly tasks on different plates, so the first plate that is very simple, general parts you can assemble. The second plate is focused on gears, okay? The third is a cylindrical kind of cylinder kind of assembly, where that actually shows different pedestrians precedence constraints from minimum to really high level, where you have lots of parallel tasks. then the collaboration between hands, or even between human and another human, or human and another robot, that's ranged from a low level of collaboration to high level as well. So this is how a detailed view of how each plate that may look like from a task perspective. As you can see on the from the left, task is from simple to very complicated. So as I mentioned, the instructions given to those 30 participants when they come in and do these assemblies is first we give them these sketches of how the product look like, exported assembly view as well. Then ask them to figure out how to put it together, okay? To our surprise, not to our surprise, they can do it really nicely. Some of them making mistakes and they have to do the rework, and we can show different kind of efficiency as well. The second stage, we give them these detailed instructions, have figures there, have the text instructions there as well, okay? Then the third stage is just do the work as you have remembered. You may want to innovate how you want to put together these products. So there's a blank instruction there, okay? So that gives us a lot of understanding around how people pose their work, how people actually make mistakes, how people actually tend to combine tasks using two hands as well. So a lot of insights from there. So these are the annotations. We labeled left hand, right hand at the very high level task level to down to finger level, how you actually perform certain actions as well. In terms of how we labeled these knowledge of assembly knowledge, we follow this hierarchical plan from task level to primitive task level, then to autonomic actions. So by defining on the right-hand side, these 9 autonomic actions, common actions you'll see in assembly, then we actually reuse these parameters for modeling any assembly task you may be conducting. This is a detailed kind of schema of taxonomy that we come up with. So that actually can be used for representing assembly plan. From the from the top left, a task will have a list of primitive tasks, then that can be decomposed into a list of atomic actions in green color. Then for each action, you ask that action can be performed by machine, can be performed by human, but there are certain parameters has to be common. That includes maybe what are the action patterns that you may be using, okay? If you want to put a gear onto a shaft, they must have the pose and trajectory, force and torque requirements of the connections as well, because those are the essential information, no matter whether it's robot performing it or human performing it. So that's the information really interesting. Want to understand the semantics and core information that drives people's work. So I'm not going to show you the details. These are all available online. So with all these annotations, and we're able to actually tell from a video clip what person is actually performing. If you look at these horizontal bars, 4 bars over there, so right-hand side at the very bottom level, you say, oh, not doing anything for a period of time, then approach the box, then grasp the box. But actually, you look at the person has been achieving at the task level, oh, the person is not doing anything meaningful at that time. So we can actually model this, okay? And really, the key drive for us then is to understand, can we actually just through video understanding techniques to really understand all this information if people just perform some of the tasks in front of you. So we benchmarked our data set against the state-of-the-art algorithms on 4 foundational techniques: action recognition, object detection, action segmentation, multi-object tracking. So you will see that the performance of the state-of-the-art algorithm is relatively low. Give you one example there, maybe not very obvious on the top left. This accuracy of all these models for action recognition, you can look at the top right accuracy. The best is Uniformer Vito, that's around 62.4%. But as we all in manufacturing understand, we need to be more accurate than this. So I'm not going into the details there. With all this foundational work, I think we can do some cool stuff. First, maybe we can monitor how people are doing precise, high quality, high value product assembly. This is very common in manufacturing in New Zealand. Okay. As this example from the left-hand side, the operator maybe put together hydraulic check valves. They've given some assembly process instructions. Then we can model this knowledge at the bottom. Then on top of that, then we align work with the instructions that they were given, then we can actually monitor with every single item that is assembling. Are they doing it right? Are they meeting the quality requirements? So this is a demonstration of the system we developed in our lab. In this, we are able to suggest immediately based on your actions what the next action should be. And then based on these timestamps, we can also understand product efficiency of that. So this is something that you are able to achieve. On top of that, many people care about human-robot collaboration. So yes, if we have an assembly task, you have instructions, the CAD files, the demonstrations, maybe you can take from other places, then follow the taxonomy we have developed. You can model the task, but then the task can be allocated to human and robot dynamically based on maybe your fatigue level, based on availability, based on preference of left hand, right hand as your dominant hand on of that. So this brings me to this summary here. I think the thinking and results show around to increase the understanding around human needs in industry. Maybe can we move up a little bit further to allow machines system to be more compassionate and in working with people. So there's increased awareness on human centricity and evolving human-machine relationship. Would like to see how diverse human-machine collaborations may look like, okay? And on top of that, maybe a little bit further research on human-machine understanding, reasoning, and evolution would be really great. So with all this, this brings me to this overall idea around where we are pushing our research to. So we want to see a super intelligent manufacturing system where things can be self-organized. No matter you are working with individual robot or systems, no matter how you are doing it as well. With this, thank you very much for your time. I'm really looking forward to some nice conversations with everyone here today. Yeah, thank you.
Hello for the wonderful sharing. Already have a discussion, but for you reach further for future.
Yes.
Well, thank you for Dr. Lu's excellent presentation. My name is Zhao Linyuan, and I'm a postdoctor in George's team. I major in artificial intelligence and its application in industrial. So I want to ask a question about large language models. As we all know, LLM is an emergent AI technique, and the machines will be much intelligent with LLM, with large language model. So if can we combine the human intelligence and the machine's intelligence to achieve a more advanced human-machine collaboration? Could you give me some outlook or suggestion? Thank you.
Thank you very much. This is an excellent question. I possibly don't have a final answer, but I understand there are multiple people in this room actually doing the research already on large language models, how they can enhance the capability of humans in maybe human-robot collaboration. I think in general, I mean, I tested existing large language models, and we also worked, have active research looking at how to extract knowledge from different modalities of sources. In my basic understanding, current large language models that can already have a good understanding of some of the common tasks or common plans, how that may work. For example, you say, how do I make a cake? If you ask it, they'll give you very precise kind of description step by step. But I believe that's also learned. That's because you learned that from the large language sources it has already got. So, but when you put large language model into manufacturing, I think into really precise understanding of new knowledge, for example, maybe that can you'll see very different outcomes from there. Give you one example. For example, we're very interested in understanding, say, can large language models understand 2D CAD drawings? Information that we all know. Engineers, you read the CAD drawings, you understand everything, right? But how do you do that? Is it accurate enough? So I think absolutely large language models and other AI techniques can actually enhance the capabilities of humans, but maybe this needs a little bit more work in combination with other approaches as well to really have these domain-specific language models that really help us generate knowledge or exchange knowledge or integrate knowledge. So yeah, for sure, there are already lots of work around, for example, using large language models to actually control robot movement. But that to me, there's more of an interface instead of new intelligence. I'm not sure whether I answered your question.
Oh, yeah, just very good suggestion. Thank you very much.
Okay.